Hi, so this week we're going to look at how we can use the resources that we have in Alberta and chemically what happens when we burn it and get the energy from there. This is a map that I found online with all the different deposits in Alberta. It also includes kind of the different pipelines that move around the oil and the natural gas to where they need to go. You'll see there's some refineries on there as well. Uh, and then there's also some other forms too of renewable energy, which we'll be talking about next week. But this week we're going to look at where some of these deposits come from, just really briefly, and then also uh, theoretically the amount of energy we get when we burn fossil fuels. So coal is mined usually in these open strip mines, and it comes from just dead plants and dead dinosaurs that over hundreds of millions of years with high pressure and temperatures is converted to coal. And so then we need to get to these deposits and mine it out, especially because the coal is a solid. But when we take this coal and mine it out, we can then burn it in a coal burning power plant. So we really, in all power plants, what we're doing is we're heating up water and producing steam. So we're heating up water here using coal in a coal-fired power plant to produce steam, which turns a turbine, and then we get electricity from that generator. So in that turbine, there's a coil and magnets, in the generator, and then we end up producing electricity. The one thing we did talk about in the first unit, we talked about acid rain and where it comes from, especially some of these sources of coal that has a lot of sulfur in it, that can kind of leave these stacks out into the atmosphere and then form acid rain. A lot of technology, when they talk about like clean coal lately, is a lot of the technology has to do within this stack where they have scrubbers and some of these things that takes these products and this exhaust and then cleans it up in that scrubber before it's actually let out, so that acid rain is less of an issue, and there's some cleaner products that are produced. The other type and of fossil fuels that we use in Alberta is petroleum and oil sands. So there's the more conventional oil, which we can drill for, and then there's also the oil sands, which is a little bit harder to extract and requires just some more technology. Now, like these forms are things that we still use quite a bit, and you'll see like in this global fossil fuel consumption, just the amount of fossil fuels that we use and how it's increasing year over year, just because infrastructure is set up for that. And also some of these things like crude oil we use for other things like plastics or other polymers that are useful to us. So when they look at the natural gas here, a main form of that is methane gas. Natural gas can be we can get at a couple of different ways depending on where it is. The one that people are talking about lately is fracking, which means they drill down vertically and then they drill horizontally, and they can put in a whole bunch of different detergents and sand, and then crack some of these layers in here, which allows the gas to actually flow out. That's kind of one way that we can get at some of this natural gas, or we can just go straight down if there's like a conventional pocket that we can just drill into. Natural gas is so those are kind of the types of fuels that we have. This week our focus is going to be on the energy of combustion, and we do have this formula in our data booklet, which is called Hess's law. Now what happens, so in a reaction, so we can have exothermic or endothermic reactions, but theoretically what we have, so when we look at this methane, we have our methane, which is CH4, and we know that in a combustion reaction we're reacting that with oxygen. Those are our reactants. Now we want these reactants, when we burn them, we want them to release their energy because that energy is going to allow us to turn a turbine or a motor in our car. So we want them to release energy. So when these reactants react, they produce products. And these products, because these reactants are releasing energy, these products have lower energy. So when we look at the carbon dioxide and the water that is produced, it has lower energy than what we started with. So this is kind of what a potential energy diagram would look like for an exothermic reaction. An exothermic reaction is a reaction that releases energy. The difference between these reactants and these products is what is called enthalpy. Enthalpy is the difference in energy between products and reactants, and we have a symbol for that. That is delta H. So this week we're going to be looking at calculating delta H. Now there is a note in your is because of Hess's law. When we look at Hess's law, what Hess's law really says, there's a whole bunch of symbols here, but it says basically that the delta H, or the enthalpy, is equal to the energy of the products minus the energy of the reactants. That's what Hess's law states. So when we look at this potential energy diagram, our products our reactants are methane and oxygen, and our products are carbon dioxide and water. Now Hess's law says that the potential energy is the difference between those. So as that chemical reaction happens, the difference between them, my products minus my reactants, is going to give me my enthalpy. Now because my products have a lower energy in an exothermic reaction, when I go this number, which is more negative than this number, I'm going to get a negative delta H. So let's look at Hess's law and how we can do that for this reaction. So we have this chemical reaction, CH4 gas plus oxygen gas produces carbon dioxide gas and water vapor, so H2O gas. It is important to note that in a combustion reaction, we are producing water vapor in an open system. In a closed container, we would actually produce water liquid, or in our cells, like in the case of cellular respiration. So now I need to balance this, so I need 2 of those, which gives me 2 of those. So I have my balanced reaction. Now, so Hess's law again says the sum of my products minus the sum of my reactants is going to be my delta H for that reaction. Now, the energy of the products and the reactants, when we talk about that, so in this reaction, I'm going to split my products and my reactants up. I'm going to find my total energy of my products. That's this total energy of my products. This means sum. And then I'm also going to find the total energy of my reactants. And then my delta H is the difference between them. Kilojoules per mole. So methane is negative 74.6 kilojoules. And that's for 1 mole. Because I only have 1 mole, that's going to be my energy. Now my oxygen, it has a value of 0 kilojoules. So it doesn't really matter if there's 2 moles of it because there's 0 kilojoules per mole. Then I look at my product side. 393.5 kilojoules. And that is for 1 mole. And there is 1 mole here, so that value doesn't need to change. And then I need to add that to my water vapor, which when I look at my chart, so negative 241.8, but there are 2 moles of that. So I need to take that negative 241.8 and double it. So because there's twice as many moles, I get twice as much energy. So that's negative 483.6 kilojoules. So now when I look at my total energy of my products, this is negative 877.1 kilojoules. Total energy of my reactants is negative 74.6 kilojoules. So Hess's law, my delta H, is my products, which is negative 877.1 kilojoules, minus my reactants, so negative 74.6 kilojoules. So the enthalpy of this reaction is negative 802.5 kilojoules. So what this says is that in this chemical reaction, when I burn 1 mole of methane with 2 moles of oxygen, I'm going to get 802.5 kilojoules of energy being released. So that's how we can theoretically identify the amount of energy we get from a chemical reaction. This week we're going to be looking at Hess's law, which is the sum of the products minus the sum of the reactants. So we have our products, we subtract our reactants, and we get this enthalpy value. This is kind of what this week's assignment will be, and this week's practice as well. The booklet, when you look at this chart, so when you look at this chart in your data booklet, you'll notice that at the very bottom it says that a negative sign means that something is exothermic, and a positive sign means that it is endothermic. Now the reason for that we're talking about is something called heats of formation, which is also in your data booklet. So when we look at this table, we have these values which are called heats of formation. What they do is they take these compounds and they basically assign potential energies to these compounds. So they take these compounds from their elements and they say this is how much energy they gain or lose. So these are enthalpies of formation, and these are what we use in Hess's law. One thing to note is that elements are given a value of 0. So we also need to keep that in mind. So I look in my chart and I see that methane has an enthalpy of negative 74.6. Now you'll notice that the unit for this too, is we go back to the chart, is an element, which means I have carbon dioxide gas. So carbon dioxide is negative. Water, this is why it's important for states. So water vapor is negative. Reactions that involve fossil fuels, things that come from this chart. But this week, 41.8. Now, this is something that even in the future, the world is going to need in order to produce energy. So this is an example of maybe potentially different energy sources in 2035. This week, we're going to be looking at calculations involving theoretical amounts of energy from oil, gas, and coal. Then in the next couple of weeks, we'll look at how we can, we'll look at nuclear reactions and some of the energy that we can get from some of those other sources.